Hello and welcome. Today is Friday. We are almost done with our second week of online schooling. Um, Good morning to everyone who's here. People still waking up. Uh, let's see. Good morning. Good morning, chat. All right. Anyway, you may have gotten the latest email. We are going to go ahead and follow what LAUSD is doing. So we've extended our school closure to May 1st. So we'll be coming back to school the first week of May. So all of April will be closed down. So May 4th, I guess. May the 4th be with us all. That's Star Wars Day. Now, next week is only 4 days of school, which from Monday the 30th to Thursday the 2nd, and then I believe the 3rd is a holiday, Cesar Chavez Day, and then we have our spring break. So from the 3rd all the way up to the 10th, there's no school, which means no streams and stuff. So you get your spring break still. We're still going to be on the spring break schedule the same way. And then we'll begin our online sessions again on the 13th of April, all the way to May 1st. So until May 1st, we'll be online, and then on the 4th, hopefully, we will get back to school and do our fun lab and projects and stuff. All right. So anyway, today we're going to start our next unit, Unit 10 on circuits. We went over our quiz yesterday, which was okay. It was okay. I mean, some of those questions were tricky, and it will be curved by three points, which is quite a lot. It's like 10%, right? So you're gonna get boosted 10%, which is nice. But it depends on where you are. If you're too low, I suppose it doesn't help that much. All right. Ow. Circuits. Let's go and start circuits. Let's see. This is our extension extension from Unit 9. Remember, we're not done with our flippy yet. The next few entries on the flippy will be about circuit elements and such. I will open up the Unit 10 section soon, but for now we will look through this PowerPoint here. Electrical circuits. Go and take out your notes. We're going to take some notes today, and we'll use a online simulation kit so we can play around with our own circuit. Unfortunately, you can't do it in real life, but we'll make the best of what we have with our online FET simulations, and then maybe watch a quick video and a clip here and there. So all right, let us begin. Electrical circuits. Hey, there's Chapito. Welcome, Chapito Bryant. Alright, so circuits. Circuits are typically drawn with schematics or symbols and designs. They kind of simplify the elements, the actual physical elements that go into a circuit. So typically, a simple circuit would be like this. This is how you turn on a light or something, or turn on your heater. And then it can get more and more complex, and until you become an actual electrical engineer or something, right? This was like a stupid joke, but we don't have time for jokes today. We'll go move on to slide number 5, which is a quick video on how rechargeable batteries work. So we talked about electrical potential. Electrical potential is some sort of value in space that gives an impetus for charges to move, really. Similar to how height works for masses in a gravitational field. Masses naturally move from a high height to low height So we can call that high height a high potential because it has lots of pegma. And so the ground would be low potential, and so naturally it moves from high to low. Similarly, positive charges would move from high potential to low potential, right? But in reality, positive charges don't really move. It's just a way for us to simplify things. In reality, it's the electrons that are moving because the positive charges are actually stuck inside the atom. So but we can always say that, you know, an electron moving to the right is mathematically equal to a positive charge moving to the left, right? Okay. So with that being said, let's go take a look at this video.
Perhaps the greatest achievement of modern man is the ability to harness the power of Zeus. The importance of controlling electricity is easy to take for granted, but electricity is why doing stuff at night is so easy, and at this point, it's what keeps the first world first. But what should be the second greatest achievement of the industrialized world gets even less attention. It's the ability to put Zeus in your pocket. The battery is the silent, unsung hero of modern man, and batteries are everywhere. Just go to a concert. The ability to store up some energy, walk around with it, and use it when you need it has had a profound effect on our lives and our cultures. The battery is what gives us instant images and
Oh, what happened? Let's see. Whoops. Did we mess up?
perhaps the great gives us instant images, and that has made things possible.
Okay, technical difficulties. Something's wrong. I don't know.
Perhaps the greatest. So, how do you get electrons? The inside.
Oops.
There are many different types of batteries, but they all pretty much work the same. Let's look at a cell phone battery. Now, to understand how a rechargeable battery works, you need to know a little background.
The electron.
This is an atom. The inside has a clump of positive charged particles in it called protons. The outside is a buzzing cloud of negatively charged particles called electrons. And electrons are the key to electricity. The movement of electrons is what makes the lights go on. So how do you get electrons to move through a wire if they're happy just buzzing around as part of an atom? Well, it turns out that electrons just want to be happy. And for electrons, happiness is being at a lower energy level. Think of it like this. Let's say a high energy level is like working at a high stress job, and a low energy level is like sitting at home stress-free. If your boss said, "Hey, do you want to work from home?" you'd do that. And if your boss said, "Hey, do you want to stay at home and still get paid for not doing work?" who wouldn't do that? Well, electrons do the same thing. For electrons, buzzing around some atoms is like working in a high-stress environment, and buzzing around others is like sitting at home and getting paid for nothing. A battery basically gives electrons a path to a happy, stress-free life, but makes them work for it, which we'll get to in a second.
The ion.
Here's the atom again. As we mentioned earlier, there's a positive charge part and a negative charge part. In a normal atom, there's balance. The number of protons equals the number of electrons. But if an electron leaves this atom, now the positives outweigh the negatives, and we're left with a net positive charge. Add electrons, and we're left with a net negative charge. These are ions. An ion is simply an atom that is no longer neutral. It has a charge because it has either lost or gained electrons. So while electrons want a low energy, stress-free life to be happy, ions just want to be neutral. And they do this by finding an opposite charge and sticking together. The heart of a battery is electrons and ions trying to achieve happiness.
The battery.
Let's look at what parts make up a generic rechargeable battery. First, you need two different materials. One that for an electron is like working 80 hours a week for an abusive boss, high energy level, and the other is like sitting at home collecting paychecks, low energy level. In other words, given the option, an electron in material A would rather be in material B. In fact, if you just put these two materials together, electrons would just hop from one to the other. They would take a shortcut. To stop electrons from taking the shortcut, you need to add a barrier that forces them to take a detour. This detour is the circuit. In other words, the thing you're powering with the battery. And finally, you need something for ions to move around in. Here's how it works. With the circuit off, electrons in material A are stuck in their high energy, high stress atoms. Out of reach and on the other side of this electron barrier are material B atoms, which would offer an easy, cushy, low energy level position. Let's turn the circuit on. Now you've offered electrons a path to happiness. Since they can't go any other way, they begin flowing through the circuit to material B. Back at material A, the atoms are losing electrons, because that's where the electrons are coming from, and they begin turning into positively charged ions. As we mentioned before, ions always want to be neutral, so these guys need to find a negative charge. So they go to where the negative charges are, in material B, where all the electrons are going. You'd think that these ions would just meet up with their lost electrons and become neutral atoms again. But unfortunately, the electrons are way happier where they are now, so the ions have no choice but to kind of mingle with the atoms of material B. So what we've got is kind of a mishmash with B atoms mingled with A ions. As the battery discharges, electrons and ions are making their way from A to B. When you can't fit any more material A ions into material B, the battery is fully discharged. To recharge the battery, you just do things in reverse. Instead of a circuit, you're putting an energy that forces the electrons back into material A. The ions then leave material B and rejoin their lost electrons, and the battery is ready to discharge again.
Yeah, so the last part is where you're using something more powerful of the recharger itself to push the current or the flow of charges the opposite direction, so it loads up the battery back up again. Now it takes some time. Not only that, you don't always get 100% back. You lose some. Some of it stays on the right side in that diagram. And so maybe you get 99% back, and then you discharge it again, and you get 99% of the 99%, and so on and so on. And eventually you just trickle down, and when you try to recharge your battery, it doesn't actually charge up all the way, right? Your battery might be stuck at 97% instead of going to 100. And so what do? Well, you get new software updates that tricks you into thinking that you have 100%. So that's that. So the way to fix it is to trick you into thinking 97% is the new 100%. Yeah, they do. So there's this life cycle. Basically, certain batteries can be recharged, let's say 10,000 times, and after that, after always doing 99.9% of 99.9% over and over and over, it just goes down too far low to be fully functional, right? You might, instead of lasting you your laptop batteries are supposed to last you like 8 hours for the whole school day, but as you know, they don't. And the longer you use that laptop, the less the battery life you have. Is that why batteries deteriorate? Yes. Because when you try to push it to go the other way, some of it gets stuck and not all of it goes back. All right. So there are a couple of terms that we need to know going into circuits, and these are similar to terms we've talked about in electrostatics. So voltage, now it says it's like a force. It's not really a force. The force is the electric force. Voltage is more like the potential difference, right? Delta V. If you recall, we did KQQ over KQQ over, no, V is K single Q over R. There we go. KQ over R. That was the potential at some point in space, some distance away from Q. Right. And so if we have two different spots in space and we measure the difference between them, the delta V, that's what we would call voltage. So what is a voltage in the real world? Well, there's a potential difference between the top of the battery and the bottom of the battery. Let's go to our drawing view. Now when you draw a battery, if you've noticed, there is, hey, we have a new follower, welcome. Make sure you hit the follow button, it's free, so you can type in chat. If you have a battery, recall that batteries are typically cylindrical shape, technically it's based on what type of battery you use, of course. But the ones that you normally use, like the AA, the AAA, even the quadruple A battery that you have in your stylus, okay, have the same shape, essentially a cylinder, and then there's this little dimple thing at the top. Okay. So there's this dimple thing at the top, and then the bottom is nice and flat. So chat, which side is the negative side of the battery? If you ever looked at the packaging or the wrapping, it actually tells you which one is plus and which one is minus. This course low-key heat. What? You mean? Oh, I get it. You mean it's fire. Can we get a fire emote somewhere? Christian Tran says bottom is negative. Chapito agrees. Yes, very good. The bottom is the negative side. The flat side is the negative side. And the top with the little dimple thing is the positive side. Now, when you insert your... There we go. There's the fire emote. Excellent. When you insert the batteries... so make sure you pay attention. Typically, you're squeezing it into like a spring thing. So when you insert a battery, the spring is pressed against the flat side. So you apply some force. So make sure you never put the battery in reverse. I've had this happen all the time, especially when we did labs and stuff. But now that we're doing like virtual labs, I guess we won't have this mistake. Dimple side has more stuff, so it means positive. Oh, great. Fire. Ooh, I like this high res version Christian Tran has. Very cool. That's like HD 1080p emote right there. Giorgio and the goat have the lower end version, I guess. What is this thing called? It says curse lit. The other one is, I don't know. Actually, the other one doesn't tell me what it is. Okay. All right. Anyway, bottom side is where make sure the contact point is the spring side, and then the top side is the top side. All right. Have you looked at how many volts these type of batteries give you? They're actually all the same. How many volts? How many volts? How many V does it say? AA, AAA. Doesn't matter if it's Energizer or Duracell. If it's this size, it has a certain voltage, and it's purely due to like basically the chemistry inside of it that gives you this voltage. So you have alkaline batteries will give you this voltage. No one? Oh no. Well, if you haven't noticed, a single AA or AAA or quadruple A. Oh, there we go. Chapito. Got it. It's 1.5 volts. Yes. All right. So 1.5 volts. That means there's a difference between the top side and the bottom side. And if you measure this delta, this is technically delta. Oops. Let me write it here. Oh no. This delta V from the top side to the bottom side is worth 1.5 volts. What does that actually mean? Well, depending on how you set up your circuit, you can kind of rearrange where the 0 point is. But to simplify our calculations, we just assume that the bottom is 0 volts, and therefore the top side would be positive 1.5 volts. This is kind of an assumption, but it does make it easy. It's similar to how we did gravitational potential energy. Can I use the bathroom? Ay. Just hold it 30 more minutes. Don't have to do the pee-pee dance. Anyway, so we set the bottom to be 0 volts and the top to be 1.5 volts, so therefore the difference between the top and the bottom is 1.5 volts. Similar to how we do gravitational potential energy, in that the ground is set as 0 height, 0 meters, and then anything above the ground is positive height. Therefore, when you come back to the ground, you have 0 potential energy. So that model helps us kind of simplify circuits as well. This is how I feel when I left Kahoot Quiz Bowl. Which one? The the electrostatics one? Yeah. All right. So anyway, we set the bottom of the battery to be 0 volts, similar to the floor being 0 height. Are y'all actually in his class? Yes, these are my students. Well, we have a random. I didn't know we had a random. Welcome. We want everyone to learn physics, so welcome to our stream. Cool, cool. All right. Moving on to our PowerPoint. Okay, so similar to how naturally positive masses, or masses in general, move from high potential to low potential, high height to low height, our positive charges will move from high potential, which is high volts, to low potential, low volts, right? So it's not, these positive charges that are here at the top want to go downwards, but they can't. Remember how there was a barrier, the electron barrier, or whatever it was in the video. So there's this barrier here that doesn't let them pass. So what is one to do? Well, you're going to look for a scenic route, some other pathway, which we call the actual circuit, so that you can actually travel through wires and through elements, through all the trials and tribulations of life to get to your destination here. So that's what circuit is. Circuit is life. Life itself. All right. So that's voltage. It's a separation in potential. And then our second term, boom, is resistance. Yes, resistance. Not everything comes easy, as we all know. There's always things in our way, in our pathway, that stops us, that slows us down, that we have to kind of circumvent or jump over, hop, skippity, jump over to get through it, right? For some of you, that resistance may be this class. It's in your pathway to becoming something else. But we can't let it stop you. We just gotta accelerate and move forward. There's only going forward. There's no going backwards. Resistance, the friction that impedes flow of current through the circuit. Okay. Oops. In a river, if we continue this river thing, of course, falling from a high height would be the natural progression of water, and as the water keeps going through these rivers, there may be rocks in the way, and these rocks will slow down the velocity of the water molecules, right? Similarly, the resistance in a circuit slows down the flow itself, the flow of current, so there's less things that can move through. The resistance, you can also think of it as like an accident on the freeway, and as soon as something happens on the freeway, like the 5 freeway or the 101, right, everyone feels it. Not just the people who are near the accident, but everyone else who's trying to go to school or go to work that are like a mile away might feel that slowdown in the flow. Okay, so when you put a resistor in a circuit, it affects the entire circuit in that it slows down the entire current flow in the circuit. Okay. All right. So of course we know that voltage is measured in V volts. Okay. Resistance is measured in omega, and this stands for ohms. Ohms. There we go. And so resistance is measured in ohms. Okay. All right. So a new unit, omega, capital Omega. Do you go to school? Oh. I don't think this person is from Elko, so he's just a internet person who likes physics and joined us. I'm guessing. All right. So omega is our new unit. It's ohms, and this is how we measure resistance. Now, what is a resistor? What does it look like? and I'll show you with a simulator in a second. Some old-fashioned resistors look like a little tiny dumbbell, very small, and or like a doggy treat, a doggy bone. Okay, and they have little stripes of different colors, and the stripes will tell you what or how many ohms of resistance each thing has. Okay, I've heard of ohms. I'm from Texas. Oh, cool. All right. So anyway, we don't have to know the color bands. If you'd like to learn about the color bands, consider becoming an electrical engineer like Aryan, wherever Aryan is. Consider learning these stripes, Aryan. But we can represent this as a circuit symbol. And the circuit symbol is very simple. It's a little squiggly thing. So jaggedy squiggly thing here. It doesn't matter how many jaggedness or how many mountains and valleys you have, trenches. It's just a little squiggly thing, and the squiggly thing represents some sort of resistance. That means things want to move forward like this, but they can't. They have to go through all this trouble. It's almost like if there is an accident on the freeway, you know how you have to like turn and curve from lane to lane to not step on broken stuff and all that jazz. So similarly, we use that concept as the symbol for a resistor. Anything can be a resistor, really. But some things are obviously better at resisting flow than others. Okay, so if you use your vocab words from the last unit, a conductor, something that allows electrons to move freely, would be a terrible resistor, right? So conduction and resistance, or conductivity and resistivity, are actually inverse of each other. So we need materials that are more insulating in that it stops the flow of current, stops the flow of electrons. But we don't want like really good insulators, because that would mean nothing can move through. So we have to be somewhere in between, something that sort of lets current flow, but not as much. So a resistor is kind of in between a conductor and an insulator, closer to being an insulator than a conductor, but somewhere in between, something else. Any wire, so let's say any metal wire, can act as a resistor. So let's say this is a wire. It's a big wire, huge, and it's made of metal. Okay, each metal has its own property called a resistivity. It's based on the chemistry of the atoms inside of this metal. So this weird little symbol I have here, this is rho, R-H-O, that's how you say it. Okay, rho. We did use this for density at one point. A parent that is strict but not too strict. Ah, excellent. Yes. Good job, Giorgio. Okay, so circuit symbol for resistor. Resistor. Rho is called a resistivity, a physical property. Physical property of the metal. Okay, of the metal. Similar to the K value of springs, when we did springs, remember how different metal springs would have different K values, which would mean that they stretch or compress different amounts, right? So if you use copper or you use nickel, or if you want really good wire that has very low resistance, you would use like gold or silver. Silver is actually better than gold. in conduction, but it's more likely to corrode. You can actually buy gold-plated HDMI cables to show off. They cost like $2,000 or something ridiculous. But gold, it's a very good conductor, and it doesn't corrode as much, so it'll last you, I suppose. But it's also going to burn a hole in your wallet, so that's for you to decide if it's worth it or not. Alright, so resistivity is a physical property of the metal. Based on how you shape it, the wire has a certain area, a cross-sectional area, area A. Okay, such a flex. It is a flex. It's really a flex. Sorry, I missed some stuff. My desktop turned off itself. Ah, well, Christian, no worries. You can always go back to the video. You know how to do that. It's at the top, and you can catch up time travel by skipping a little bit. Area A. Okay. Now, if it's nice and circular, how do we find the area? Well, we need to know what the radius of this thing is. So it has a certain radius r, and if I know what that radius is, the area would be pi r squared. Okay. All right. It's only pi r squared if it's a nice circular cross section. So if it's a cylindrical wire, I can't speak today, cylindrical wire, and you cut the wire, you'll see that the face is basically a circle with some radius r. Okay, and the wires also have a certain length, L. Okay, and you can of course control how much you want, and by putting all this together, we have the resistance equation. R, which is the resistance, is equal to this constant rho. So here's another constant. It's based on the material. If it's copper, it's some value. If it's nickel, it's some other value. These are things that you don't need to memorize. It's either given to you or you're solving for it. So it's rho times. It turns out the longer your wire, the more resistance you have. That's because imagine trying to go through this. And if it's a much longer wire, you're going to crash into more atoms, which means it's going to slow you down. Therefore, the longer the L, the higher the resistance. So rho L. And area has the opposite effect in that the bigger the area, the less resistance. So you can think about area as like opening up more lanes on the freeway. Of course, if you have more lanes on the freeway, you're going to get more cars going through. So more things can pass through if your area is bigger. So therefore, A is in the denominator. So that when A increases, when the denominator goes up, the actual value of the resistance goes down. R is resistance, and it's measured in ohms, omega. L is the length of the wire, measured in meters, m. A is area of the cross-section, area of cross-section, measured in meters squared. So you have to convert all of your units to SI. And finally, this new thing, rho, the resistivity, which is the physical property of the metal. Oops, not resistance, it's resistivity. And the units are ohm meters. Ohms times meters. Ohm meter, an ohm meter. Okay. Now, how do we make sense of this? Well, if you don't like cars, you can think of it as water or something. Here's your hose that you're using in your garden in the back, right? So if you have a big giant pipe or a hose, you're going to get tons of water gushing through, pew, 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 pew. So increase flow. Whoa, more water per second. Okay. And of course, if you kind of squeeze it or you shrink it, you get less water, etc. Or I shouldn't say squeeze it. I should say if you had a skinnier hose, like a tiny little garden snake-like hose, then you're only going to get a little bit of water per second. Right? So when you break a fire hydrant in the summer or something, I've only seen this done in the movies, and you get like tons of water gushing out, right? And it creates these huge waterfall or water jets, I should say, up into the sky. Okay. All right. So resistance is slowing us down in our circuit. Resistance is slowing us down. And the last thing is called the current itself. The current is the flow, the actual thing that is moving. Of course, in the river, you have water molecules that are moving. In our circuit, we have electrons that move. Realistically, electrons are what's moving. However, to make the mathematics easier, or just to not worry about the negative sign of electrons, really, what we do is we think about a positive charge moving in the opposite direction instead. Okay, that's because electrons, remember, do the opposite of what positive charges do. Not like when we compare it to gravity, we only have positive mass, which is mass, and masses move from high potential to low potential. So it's natural for us to think about how if I drop a pencil from my table, it drops onto the floor naturally because gravity pulls it down. Similarly, a positive charge would be pulled downwards by the electric force from high potential to low potential. Whereas if we start thinking about electrons, it would be as if like my dropped pencil that's on the floor naturally would just move upwards onto my table, which is hard to believe, and because it doesn't happen. But that's what electrons do. Remember, they're like salmon migrating up a waterfall. They go up the gradient instead of down the gradient. So to make it easier on us, we imagine pseudo-positive charges moving through our circuit. One note. Current, resistance. So V is voltage, V, measured in volts. Resistance is R, measured in ohms. We have I, which is the current. And it's measured in amps, A. Amps. Now amps is short for amperes. Amperes, no, amperes. Resistance is futile. Very funny. Current measured in amps, A. Okay. Now what is current? Current, I don't like that. Let's try again. Current I is how much charge you're getting per second. So current is essentially the amount of charge, delta Q, over delta T. Okay, charge per second. Remember, Q is the variable for charge. So this is measured in coulombs, charge in coulombs. And this is time in seconds. Coulombs, capital C, seconds, little s. So essentially, 1 amp, 1 amp is equal to 1 coulomb over 1 second. Okay? You get 1 coulomb of charge every second if you have 1 amp of current. That's actually quite a lot, right? How many electrons is 1 coulomb? Anyone remember? It was on the quiz, right? 6.25 times 10 to the 18th or something like that. Or is it 17? I can't remember. Chat, help me. Was it 10 to the 17 or 10 to the 18? Well, how do you do it? Well, you take the inverse of the charge. So 1 divided by 1.6 e negative 19. And that should give you 10 to the 18. Yay! So that's 6.25 times 10 to the 18 amount of electrons every second. So that's quite a lot of electrons. And so in your circuit, you don't really have like an amp of current flowing through. That's quite a lot. So we use resistors. Excuse me. We use resistors to slow it down, to lower it. I'm talking way too much. The throat's getting dry. All right, so current is charge per second. Coulombs per second, I should say. It is a flow of positive charges. So this is current, or it's also called conventional current. We call it conventional because we made it up by convention. Flow of positive charges from high potential to low potential. Okay, remember potential is V, the volts, so from high volts to low volts. And you want to compare that to being, high up into the mountain to low onto the ground. So naturally, your positive charges will move from high height to low height. Okay. Whereas electron flow, the actual electrons, actual electrons move from low potential to high potential, move in reverse. Okay. All right. Okay, so we'll stop the note taking there, and we'll come back to it. But let's go and pull up a simulator, a circuit simulator that will help us kind of build our first circuit. If you go to your FET physics, if you just search FET physics, it's really the first one. FET simulations. I don't know why the pictures are all weird today, but that's all right. You click on electricity, magnets, and circuits. Electricity, magnets, and circuits. And it's this third one here that says Circuit Construction Kit DC. Circuit Construction Kit DC Virtual Lab. And it is in HTML5, so you should be able to open it. Circuit Construction Kit DC Virtual Lab. Click and then hit play. Voila, we are now in our circuit lab, a virtual lab. And using this, we can build our very first circuit. So you can see how you have stuff on the side here. You can just drag and drop them. First, I need a power source, because without a power source, nothing will be moving. So here's our battery, and we can even rotate it and orient it whichever way we want. So let's put it this way. Here's our battery. And if you click on it, you can actually change the values. So apparently it's a 9-volt battery. We'll keep it there. Alright. We have wires, and ideal wires, like the ones we have in our simulator, ideal wires actually have 0 resistance, right? But in reality, all wires have some sort of resistance. Even the best conductors, even if you have silver wire, it's still going to have a little tiny amount of resistance. But when we do our math and we have wires, we're going to say that wires have 0 resistance. Therefore, whether the wire is tiny or really long does not matter, because we're just going to say that the resistivity of the wire is 0. Therefore, 0 times L divided by A means nothing because it's still 0. So we can basically stretch out the wire as much as we would need when we're building a circuit in the simulator, because it will not affect the actual resistance, the actual flow in the system. Right. Next up is a resistor. This is what a resistor looks like. Whoa. And it has little bands, and the bands tell you the actual value of it. And if you click on it, you can change the value. This is 10 ohms. Okay. Typically it's 3, and then there's this fourth one that tells you like the precision of it. Sometimes it's within 5%, sometimes it's within 10% of the value. So if you're getting a 10 ohm resistor, it might be 10 ohms plus or minus, 1 ohm, or sorry, 0.1 ohm or something. So it could be 10.1 or 9.9, and when the manufacturer makes it, they're guaranteeing you that it's within that range or something like that, based on what color bands you have at the end. All right, and if I change the value, you'll see that the colors change. Whoa! Right, here's 120, brown, red, brown. Okay, and this last one, this gold one here, doesn't change. That's the precision one. All right, let's just leave it at 10. Instead of using a resistor, well, let's see. I'll do the other one next, but we could also use a light bulb, and we'll talk about that in a second. But here's a resistor. We connect it. Pew. Now nothing is happening. That's because there is no circuit, in that there's no closed loop for the electrons to go from the top side of the battery to the bottom side of the battery. So we need to close our system. Okay. Oh, there's a switch. Look, it's a switch. We can attach a switch and finally attach the battery to the switch. Oh no, it's still not working. What's happening here? Well, I need to turn it on. So when you flip a switch at home, when you flip a switch, it's like a drawbridge. Right now the boats are passing through, so the bridge is open and the cars can't flow. But when you close it, pew, and now the current can flow. This is what you're doing when you flip a switch. You're closing the circuit so that the current can flow. Okay, these blue things are electrons, as you can see on the top right. This is showing you electron flow. But we don't want to see electron flow. We want to see current flow. And this is our, conventional current. By convention, we've established that we have positive charges that are moving from the positive side, the top side of the battery, to the minus side of the battery. Okay, and then it goes through the resistor and then back to the bottom. Now, what does the resistor do? Okay, well, the resistor uses your electrical potential energy. Remember, your charges have potential energy, and it uses up that potential energy and converts it into heat. Resistors get hot when they convert the electrical potential energy into thermal energy. Okay, so if you have an electrical heater, you'll see that when you connect it, the resistor, which is the metal thing that's inside, gets hot. It starts to even glow. You could probably see it if you have an electrical heater. Or an electrical stove top, the little weird spiral thing that you see up top, heats up, it glows. That's because it's using electrical energy turning into thermal. And then when you put your pot and pan on top, through conduction, you're transferring the heat. All right. So resistors get hot. Heaters get hot. Electrical stovetops get hot. Some metals get so hot that they glow really bright, and that's what we call a light bulb. So light bulbs are like resistors, in that they get so hot that they glow. They give you, eventually, instead of just thermal energy, they give you luminous energy, which is light energy, and so shoots out photons, right? Regular resistors have a very faint low glow. You can kind of see like an orangish, reddish glow, not much light. Whereas an actual light bulb, based on the filament that they use, a traditional light bulb use tungsten, which is an element, capital W, or Wungsten in German, Wungsten, tungsten, and that tungsten filament will glow really brightly, giving you light. Of course, now we have LED light bulbs, and we'll talk about LED some other time, which is much more efficient in that it requires less energy to give you, equal amounts of light. Whereas traditional light bulbs heat up, and that heat is lost to the atmosphere. Instead of being light, it is heat that you can feel. Um, so traditional light bulbs are very hot when you try to touch them after they've been on, whereas LEDs you can easily touch them because they're cool. They don't use up or they don't waste the electrical energy turning it into heat as much. They convert it faster and more efficiently into light instead of heat and light. All right, well, I think that is all. You should play around with this simulator as much as you can. We'll be using this to do some virtual lab activities in the next few days, so get acquainted with it. I think that's enough for today. Thank you for tuning in. I'll see you next week. Bye-bye.